Okay, thank you. Evening. Let me introduce myself. I am Dr. Bab Kumar Ghosh, Senior Lecturer in the Faculty of Engineering, University Malaysia, Sabah. Today, I am going to present my work, Advanced Transparent Semiconductor for Optoelectronics. So, transparent optoelectronics is a new branch of optoelectronics and electronic systems where the flexible electronics and related technologies like building integrated photovoltaics are developed using these materials. So you know that the semiconductor materials has diverse band gaps from ultraviolet until infrared. So we try to develop the transparent devices using zinc oxide and then the silicon germanium nanocrystalline materials developed on both ITO glass substrates, and the P contact is made by the organic materials PTAA. So here you can see the zinc oxide in the ultraviolet regions and silicon germanium actually, though it is in the infrared region, but with nanocrystalline materials interface with the silicon dioxide can make it transparent bands or higher band gaps. So we are going to describe the significance of the silicon germanium nanocrystalline materials high bandage for the transparent photo device applications. Here I can see that normally the lower bandage materials has higher bulk mobility or carrier transport properties that eventually make successful for better optoelectronics and electronic devices application. So here we choose the well-known silicon technologies with the higher carrier transport property germanium as silicon germanium. That 4-4 combination is very useful for minimize the defect that can lessening the leakage current. At the same time, it can support the very advanced indium gallium arsenide related bandage for the photo device or photo detection technologies. So these are the properties that is better for 4-4 materials as a covalent bonding materials. So device primary structure, you know that the P and N-type material that is due to the exposure of light that generate the electron that move back to back towards the electrode for current development, and that is the optical energy transfer into electrical energies. In that framework, that device with the current generators and with the ideal diode condition with highest shunt resistance and lowest resistance will be the best combination for the photo devices with better sensing qualities. So our work significance is our silicon germanium nanostructure used on ITU glass substrates using the PTAP contact materials, actually more advanced silicon germanium nanostructure for transparent device application as compared to the zinc oxide PTA materials. That is our recent research. We compared these two materials as the transparent technologies. So third generation transparent solar cells, our current research, actually couple of years before we did using RF spattered zinc oxide on I2 glass substrate, followed by the spin coating method PTA material developed, and the schematic of the materials as a planar heterojunction can see at the right side here. So the materials interface and the surface properties you can see here, that is the same configurations. And then why we should choose the planar heterojunction? Because the planar heterojunction has shown better open circuit voltage compared to the bulk heterojunction material that is usually used for the organic material. That's why we implement the planar heterojunction technologies for both zinc oxide PTA and silicon germanium PTA materials for our RF spartan device technologies. So the device core characteristics is actually should lower the reverse bias current compared to the forward bias, and that is the highest can achieve the better signal noise ratio and highest rectifying ratio. That is idealities for this photo device applications. So the reverse current actually the detrimental that can reduce the signal noise ratio, and it can be less efficient. That is actually not essential for the device application. That's why we want to reduce the device leakage current by promoting shunt resistance or grain size of the materials, and then that should be done by annealing, that the recrystallization of the chrome materials that can make barrier greater, and then the interface design for the carrier selective contact that can make higher barrier for the leakage impediments, and that will be effective for the greater signal noise ratio or rectifying ratio. That is our hypothesis in this research. So how theoretically they are related, because ideality factor, barrier height, and the saturation current with the device current, how related with the junction barrier voltage and the temperature effect, as well as the cross-section areas with the current densities. It can be seen here. Definitely lower uh, saturation current or dark current definitely should be higher barrier, and that eventually can make better devices with lower ideality factors and better performance as signal noise ratios. So what is actually significant? You can see here the two graph, that one is almost horizontally flat and vertically steep, another is inclined in both horizontal and vertical states. So the first graph, if we see that the device's series resistance is lower, definitely it will be flat in the small range, and that can make better performance for optoelectronic devices. The second one is the high series resistance that can make more steep in this line of two. And then the same graph of number one, you can see that very steep and vertically the voltage changes, it's very minimum. That means it has the highest shunt resistance, whereas the inclined one is the lowest shunt resistance that can ensure better leakage, and that is poorer qualities of the device due to the signal noise ratio relationships. So in that perspective, the zinc oxide PTA materials, we don't have to develop any barrier because there was a impediment to do so. That's why we eventually use this crystallization process with the annealing temperature, and how the grain size improvement can increasing the barrier height we can observe from these two graphs at different temperature of chrome and different spin coating process. But whenever we see in the leakage current, the barrier height or grain size does not impact specifically for the leakage current reductions, because we guess that it is due to the lacking of the interface barrier layer introductions, and that's why we get the rectifying ratio in the devices. That is actually, we found the transparencies of highest. That is actually our significant transparent electronic devices. It is almost 85% transparent. That is very standard for the transparent device fabrication. But whenever I see the IV characteristics, you can see that the forward and reverse current actually almost similar from the dark laminations. It means that the rectifying ratio is not significantly increases, though the ending temperature is increased, and though um, there is no significant barrier issues between the zinc oxide and PTA materials. That is the only option that lessening this rectifying ratio, and that eventually make poorer signal noise ratio of the devices, ultimate devices. That's why we introduce the silicon germanium materials and the nanocrystal, that how it can make with the silicon dioxide interface and get a band is as a nanocrystalline configuration, how it can be support for the advancement of transparent photo devices, because we know the silicon germanium band should be less than one, but with nanocrystalline formations using these technologies on I2 glass substrate since the higher band is, and it will be seen later that our systematic design for the software-based silicon germanium PTA development and analysis, and then the real fabrications, its process flow, and the schematic of the planar heterojunctions, hybrid silicon germanium and PTA can seen at the right here. So the technologies behind this design, actually hypothesis and methodology is like that. this gap simulation we did for the low cost device fabrication, because silicon emitter design is very costly and very high temperature. That is defect prone. That's why we use the PTA materials on silicon germanium. And in this process, actually, we compare both silicon and silicon germanium with the ITO glass substrate, that how they can develop different qualities of materials and different photo responses, because silicon germanium definitely has the highest absorption compared to silicon. So high electrical and thermal conductivity PTA was used eventually as a P-type contact material on silicon germanium as a N-type, and silicon as also N-type material. So in this course, there is a silicon dioxide interface developed between silicon germanium and PTA, and their impact was analyzed in our research. So theoretically, we know that the absorption of silicon germanium is 100 times higher than the silicon, and that is very impactful for introduce greater current density. And that is actually we realized in our research here, that the current density of silicon germanium is huge compared to the silicon nanostructure material developed on PTA contact with the ITO glass substrate. And that is the highest current density that eventually make highest efficiencies of the photo devices that we analyzed in our research. And the impact of silicon dioxide as a prominent passivation materials on microelectronic technology we introduce here. And technically it can be seen that the silicon germaniums with the barrier of the silicon dioxide can make highest compared to the silicon, and that is make the impediment of recombination of electron at the interface of PTA and silicon germanium compared to the PTA and silicon, because here barrier height is less, and that eventually make greater current density with the leakage coefficient is lower. So the silicon germanium PTA's quantum efficiency, if we can see, then you can realize the differences. You can see that the top two is actually silicon germanium PTA quantum efficiency, and the bottom two is the silicon PTA devices. So quantum efficiency all over the spectrum is very, very high compared to the silicon PTA. And even it is higher for the introduction of silicon dioxide interface, that you can see that the blue line is the silicon germanium with the silicon dioxide interface. And here also the green line for the silicon with PTA of silicon dioxide interface. So that is actually signifies the silicon dioxide passivation by carrier selective barrier significant, and also it realized the differences of the silicon germanium quantum efficiency compared to the silicon nanostructures. And we realized that the nanocrystalline relationship of silicon germanium with our AFM characterization, then XRD characterization of different orientation of silicon germanium, and then eventually the absorption spectrum can see that it is greater than 4 electron volts. And it is also for the absorption and UV spectroscopy analysis, the transparency is more than 80%. So all this data realize that the silicon germanium materials developed on ITO glass substrate, it has the highest transparency and diverse orientation of very small grain material. Realize that it is nanocrystalline, and that is also counter assessed by the XRD of the diverse nanocrystalline orientations of this, and also the absorption material. So it eventually proved that the silicon germanium we developed as a nanostructure on ITO glass substrate, that is actually nanocrystalline materials and with higher band gap. That's why it is transparent, and its orientation of the small grain crystal actually diverse. That can be realized from AFM and XRD analysis. And the most impactful relationship of this both the transparent devices, as you compare the zinc oxide PTA and silicon germanium PTA, you can see that the rectifying ratio of silicon germanium in respect to the zinc oxide is very high. Here almost the forward and reverse current direction almost similar, but here forward current is very high compared to the reverse current, that determine that it is the highest rectifying ratios, and that is ultimately most impactful for the development of photo devices. Because silicon is well established microelectronics materials used as also optoelectronics, then silicon dioxide as a robust pacifier that can make signifies of this materials technology to make it higher forward current density or higher rectifying ratio. So conclusion is the barrier height or carrier selectivity is very important. Along with that, annealing condition to decrystallize the materials and ensuring the higher barrier for this recombination avoidance purpose, and that eventually make the greater uh, rectifying ratio, or ultimately the device should be more as high signal ratio noise ratios, and that can be eventually make better and design the transparent photo devices for advancement of transparent flexible technologies. So overall, the architecture, materials, and their synthesis are the key for the development of optoelectrical performance of hybrid heterojunction devices. Thank you for your listening. Thanks all. That's all from my side. This is the references you can get available in the system. So thank you. So these are all from my side. So this is the